Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on foundations of cyber physical systems. So, in the last lecture we have been talking about Lyapunov stability and the stability theorem, and from there let us go ahead with the proof of this theorem. So, if you see, this was our claim here, that as long as I can figure out Lyapunov function which satisfies this condition and this condition, that it is positive with time always, right, and it is 0 at the origin. So, yeah, it is 0 at the origin, it's positive everywhere else, and its gradient is negative, right. As long as that is true, then we can say that x equal to 0, the origin is stable, and if further this is strictly less than 0, and then we can say that this is asymptotically stable. So, kind of let us go about proving this. So, if you remember our stability requirement, in the first proof we need to show that the system is stable, right. That means, we are given the outer ball of radius epsilon, and we need to show that there exists a time point t naught, beyond which the system must be going inside an inner ball of radius delta. So, this essentially means that given this epsilon, I should be able to compute this delta and time, right, after which it is inside delta. So, as long as I can show that, then I can say that, well, this is stable, right. So, suppose I am given this epsilon, my objective is to compute this delta. So, what we do is, first we will choose a smaller value r, which is basically something smaller than epsilon, but greater than 0, of course, right. And with this, so let us say this is my domain of definition. This is my D, okay. This is the origin, and I have this sphere of radius r, some B r, okay. Let us say this is radius r, okay. And then, so we can say that B r is, I mean, we are formally defining this, it contains all those points in R to the power n such that the norm of x is less than or equal to r. So, that is the definition of this sphere, right, and it is of course contained well within this domain of the system, okay. Now, what we will do is, we are assuming that such a Lyapunov function V exists, right, with all those desired properties of being 0 at the origin, negative or equal to 0 in its time derivative, and being positive everywhere, right. So, let us evaluate this function everywhere on this circle, okay. So, all I am saying is that, well, these are all I mean the positions on the circumference, okay. On all these positions we can evaluate this function V x, because it is defined everywhere here, and take the minimum value, okay. So, let this be given by some alpha which is minimum So, you are taking this radius and you are taking all points which lie on this radius and you are evaluating V x on them, and that minimal point is what we call as alpha, right. Now, you choose a value beta which is between 0 and alpha, okay. And then let us define another inner set of this sphere Br, okay. So, you are defining like this, these are the points, these are those points of Br for which Vx is less or equal to beta. Now, let us understand why we say that this is definable, because what we have done, we know that well what are the points which are lying on this on the circumference of Br, right, because for all of them the system norm is equal to r, right. So, it is a 2-dimensional system, let us say then we are talking about all x1 x2 such that x1 square plus x2 square equal to r, right. And for all such points we are saying that well let's evaluate Vx for all those points and see that what is the value of Vx, right, and then you will get that value, right. This can be computed, and once this is computed you just take you just take any value between 0 and alpha. Now, once we have done that, we know that well these are the points where Vx is being computed, and the minimum value among these points where Vx is computed, that value is alpha. And now we are saying that we are trying to define this set beta, this set omega beta, saying that well we are considering all those points of Br, this sphere of radius r, for which the value of Vx is less than beta, okay. Now, let us say this gives me a region like this. So, this is my omega beta. Now, the question is well why should omega beta be inside R? How do I have this guarantee of, and I should be able to draw this picture? The guarantee is because let us say I do not have this to be completely inside Br. It is also containing some points which is beyond this this circle Br. That also means in that case omega beta will be containing points on Br, then omega beta will be containing points where Vx will evaluate to alpha, right. Let us say, let us just assume, let me just draw an alternate picture. Let us say this is not omega beta, but rather something like this is omega beta. Then what will happen? I have a point here, right. I have a point here and I have a point here, which are all members of omega beta, and they are also located on Br. That means, at this point let them be x1 and let them be x2. Then for these points V x1 will be equal to some value which is either greater than or equal to alpha, right, and similarly V x2 is also greater than or equal to alpha as per this definition of as per this definition I have here, right, and that I have chosen this value beta to be such that it is between 0 and alpha. And what is alpha? Alpha is the minimum of all the points on which alpha is the minimum value Vx can assume on this circumference. So, let us understand this very clearly. I am just repeating. So, I took this sphere and I evaluated Vx on its surface, and that gave me possible sets of values, right, and among those values whatever is the smallest value, okay, the place where the distribution will dip, I am taking that as my that as my value alpha, right, and then I am choosing a parameter beta which is smaller than that, and I am defining a space omega beta. So, that is defined to be a space which is also a member of BR, okay, and for it Vx is less than beta. Now, if I say that well I am going like this, I have a issue. The issue is that well first of all I am having points where I am not inside BR. So, I am not satisfying this, and also suppose how do I know that I am inside it? I am not crossing over or I am touching it, because if I touch it then I will have points x1 and x2, right, and at those points the value of V would be greater than or equal to alpha, but we know by construction that all the points which are inside or on the surface of omega beta, there the value must be less than alpha. The value must be because beta is less than alpha, because this is an open interval here, right, and the value of Vx will be less than beta, right. So, that is how I have defined it. So, that means well this is a closed volume omega beta which must be located strictly inside this circle, that is BR. Right. So, this is inside BR, the omega beta is actually inside BR, okay, because by our definition we are looking for all those points which are less for which Vx is less than beta, and in case omega beta was touching BR, then I would have points which for which the value is greater than or equal to alpha, but by definition omega beta is only going to contain points where the value of Vx should be less than or equal to beta, and beta is strictly less than alpha. So, this thing will not be satisfied. I hope this is clear, right. So, this only says that well this omega beta must be inside BR, okay. It should not even it is kind of strictly inside BR. Now, let us observe one thing. Suppose you pick up any location x which is inside omega beta, and you say that well the system at t equal to 0 is located inside omega beta, okay. Now, we should be able to show that if that is so, then at any time in future it will be located in omega beta only. Question is why? Because you see the derivative of V over x which is a function of t is negative, right. That means the system can be anywhere, but V, when I evaluate V on the system's trajectory at some future point, it must be less than or equal to the value of V at the system's location at t equal to 0, right, because with time V is decreasing. So, the value of V must only decrease, right, and we have assumed by construction that x 0 is inside omega beta. Now, this definition says that well if x 0 is inside omega beta, then V x 0 is less equals beta. Now, by the definition of the Lyapunov function, we have V x t as less than V x 0. So, we have V x t is less than beta. Now, if that happens, the only way for that to be true is that x t is inside omega beta, right. So that means this is like an invariant set, and it is able to bind the system's trajectory, and it can say that, well, as long as the system starts inside omega beta, the system must be inside omega beta for future forever, right, because otherwise the Lyapunov functions guarantee will not hold, because the functions design is such that it is supposed to dissipate, it will only become small, and by construction all smaller values must be inside this set omega beta, right. Now further we can say that there exists delta greater than 0 So now let us kind of draw a smaller circle here, radius delta. Now this is your b delta, and since this guarantee holds for the entire set omega beta, I can write this also. Sorry. So just because we can write that if the system starts inside omega beta, the system will remain omega beta, I can, and if we take a radius of a circle such that of a sphere which is small enough, so I choose delta in such a way that the resulting sphere b delta is completely inside omega beta, then what can I say? I should be able to say that as long as system's norm is less than delta, right, x's norm is less than delta, by definition I mean, as long as for all x which are inside this circle, this sphere b delta, by definition of this sphere x norm is I mean basically, I mean x is located inside, right. So the system's norm, the norm is less than delta, right. So that means since this is less than delta, I can say that, well, I mean since b delta is completely located inside omega beta, let me just rewrite this a bit. Now, since this b delta is located inside omega beta, I should be able to say this, right, like as long as I pick a location x with this property, it implies that, well, x is a member of b delta, right. So that means x is also a member of omega beta, and then by definition of omega beta, what I have is V x is less than or equal to this beta, right. So that is it, right. I mean, the point is, the moment I am able to create this omega beta, I am able to create this inner circle B delta. That means, the point is I can create this delta. Okay. If x starts inside this, then x will be a member of, I mean it will then that means x is also starting inside omega beta, and that means in future x t is located inside omega beta. That means in future x is bounded to be inside this outer circle B r. Okay. So, as long as I am starting inside this, in future I am giving a guarantee that I will be located inside this, which is less than equal to epsilon for all t greater than 0. Okay. So that is about it. Like, we can say that I can show that this bounded region exists inside which I must be. Okay. Now, we can also show the asymptotic stability. Essentially, it means that it turns out that it is sufficient to show that V x t, I mean, it will tend to 0 as t approaches infinity. Since V is monotonically decreasing, I mean x will be approaching the origin there, right. So that is about it. That is about the proof of theorem 1, and with this we will end this lecture. Thanks for your attention.